and the operators would be such that they are non-redundant, and as I told you that non-redundant means these operators are not related to each other by the equation of motion or integration by parts. Okay. And also once we gradually proceed and look for explicit calculations, we will see the, for example, different kind of identities that we use in the quantum field theory, for example, the phase identity, okay, that are also taken care of. Means if you do some kind of phasing between the operators closer operators, then actually you will still end up writing only the independent set of operators. Okay. So that is what we are trying to do. And in this construction, what we are relying on only on two aspects. What is basically the symmetry, and as I mentioned, we have two kinds of symmetry we are dealing with. One is the internal symmetry and that is the space-time symmetry. And why I am disentangled this space-time symmetry from the internal one? Because it requires a special care because of its non-compactness, right? So internal symmetry, of course, you can do some kind of theory model building with a non-compact, but we are not doing as of now. We are actually assuming all the internal symmetries, whether it's a global or a gauge, it will be connected compact group. And I have given some example of that, for example, SUN, SO2N, SO2N plus 1 and so on. Okay. And also symplectic group and so on. And our primary focus to understand the whole business in terms of the SUN, and later I will tell you how to generalize all this composition in terms of other groups as well. Okay. Point of the hard method. And also the main important part of the for choosing those things, because they have the unitary irreducible representations which are finite dimensional.
So because we are like getting over smaller variance, the finiteness, like how does it come from compactness?
Which one?
Like the finiteness of harmony.
Yeah.
Why does it? Why would it not harmony?
Because you can think of in terms of geometry, it corresponds to the compact means this is a boundary, right? This is a closed surface, so you have a finite volume. If it's an open surface, the volume is not finite. Right? From that, geometrically you can think of that way, right? Okay. So then, apart from the symmetry, once you understand the symmetry of the system, then actually what we are doing, that is the first part. See, the choice of the symmetry is also ours, because it's up to us what kind of model building we want to do, right? For example, you want to invest in a standard model, or standard model extended by some kind of SU2 or something else. So those kind of internal symmetry part is basically your choice, in a sense that okay, you want to explain some kind of observables that is predicted from the experimental things. Okay, you have observed there and you want to explain that. So you want to understand that what kind of symmetry information is associated with those kind of observables. Okay, that's why you see for different model builders the choice of symmetries are different. Right? But what are the space-time symmetry? Space-time symmetry, rather, it's not so much flexible, because all the quantum field theory from the realistic sense, that whatever the experimental evidences from the HEP we have so far, we actually stick to 3+1 dimension. Okay, it's not like you cannot go beyond 3+1 dimension. You can, but certainly there is not much clear evidence, experimental evidences for that. So that's why we restrict our space-time symmetry to be in 3+1 dimension for this particular construction. Okay. So now, as I mentioned, that this symmetry is non-compact, and these non-compact symmetries, if you look at the representation theory, they do not offer you the irreducible unitary representations which are finite dimensional. Okay. So that's why it's very difficult to explain the representations of the quantum fields which are actually dealing with the scattering and all those things which are not finite dimensional. Okay. There are some mathematical structures are there and all those things, but when I am talking about our interest is always driven by the experiment. So if it is not experimentally feasible quantitative things, we don't consider that mathematics is important for us at this point. Okay, so our mathematical choices would be driven by the experimental evidences, if it is there, or even if it is not there, there is a feasibility to get that evidences in near future also. Okay, so that's what we are actually choosing our representations. So now, so that's the reason actually in 3+1 dimension we are working, and because a non-compact, So we will see that how we can deal with this non-compact thing, and we realize that symmetry in terms of SE2L cross SE2R, which is the chiral representations, right, also known as the wild representations. For example, if you recall what you have learned in the Fermionic field theory, you have this Dirac spinner, right, which is a 4-dimensional object, and if you use the projection operator, you can project out your psi L and psi R. Okay, so SE2L is correspond to the left chiral, okay, and SE2R correspond to the right chiral object. And there we have mentioned about only the fermion, but what we will do, that we will set up our space-time symmetry in terms of SE2L cross SE2R, and that translates not only your fermions but all other non-zero spin particles, and they will project out into left chiral, right chiral. For example, the obvious things would be like the gauge sector, like for example the stress tensor, which is spin 1, but now when you write down those spin 1 fields in terms of SE2L cross SE2R, they will transform like a 1, 0 and 0, 1. Okay, that means like psi L psi R, so you will have a F mu L, F mu R. Okay, and of course, like using the psi L psi R, you can reconstruct your full Dirac spinner. Similarly, using the F mu L and F mu R, you would be able to reconstruct your F mu and F mu tilde. So that's why at some point I think someone asked about the what are the cp-violating operators and all those things. By construction, the F mu tilde automatically comes into the picture, because actually we are working the F mu L and F mu R. So while rewriting them in terms of a 4-component object, okay, in a full basis, we have to have the F tilde, otherwise we cannot do that thing. Okay, so automatically that will capture those informations. Okay, so that was our basically the starting point, and then what we did actually, we have written down something called the Hilbert series, and if you remember, the core of the Hilbert series actually constitutes of the 2 aspects, right? One was the plethysticks, okay, and another was the Haar measure. So what is the Haar measure? So the Haar measure is nothing but is a volume element in the group space, right? It is just, so basically if it is a compact, then of course the volume element will be finite, right? Now coming back to the plethysticks, what is the purpose of the plethysticks? The purpose of the plethystic, if we compare what we did in the tensor products, what we do the tensor product, that we start with the lowest dimensional fundamental representation, or in general the fundamental representations, then we take a tensor product, and that will give me all possible higher tensorial objects allowed by the symmetry for that group, and that's how we construct repeated action of that thing. And what are these higher tensorial objects? They are nothing but the higher dimensional representations, and that exactly what we do in the angular momentum course in quantum mechanics, right? It's basically the addition of angular momentum. So addition of angular momentum is nothing but the tensile product of higher SU2 spins, right? Constructing again and again, you do that thing. But also we realized that when we talk about the operator construction and all those things, doing that thing repeatedly, and specifically if your representations are higher dimensional, manually doing or just the visually doing that could be erroneous. So we can end up writing something which is not present, or overcounting, or it can be undercounting also. So that's why we need a very robust mathematical treatment such that we can make sure that all the tensor products are basically being under considerations. Okay, and that is what the plethysticks is doing. So plethysticks is basically function of the characters, right? And what are these characters? These characters are basically correspond to the representations of those particular dimension, right? So now if you exponentiate the character and you expand them, it's basically you generate different kind of functions of different order, and this scalar multiplication of these characters actually ensures that basically you are not missing out any kind of equivalent tensor products. So in principle, before even performing to understand which are allowed by the symmetry invariant or not, our task is to, for any given symmetry, for any given representations, okay, we should be able to construct all the allowed tensor products. Okay, that's what each plethysticks are doing. Now there is not a single field, there are multiple fields, right? And so each has a plethysticks, right? And when you expand them, now the plethysticks expansion give you all higher dimensional representations of that particular symmetry, okay, and when they are talking to each other, okay, they can create further singlet representations or non-singlet representations, okay. So basically the plethystis gives you a soup of basically the representations in the form of the characters, which are basically scalar functions. And because they are scalar functions, I don't need to worry about their commutation, anti-commutation, their field theoretic behavior, whether they can pass through each other or not, because this is a scalar variable, right? Now, from this soup, our target is to project out some specific objects, which we call the invariants, okay? And there the Haar measure comes into the picture. And we are using the notion of the orthonormality of the character functions. Okay, remember over the d mu, where the d mu is the Haar measure, or the d mu integral chi L chi R is basically delta LR, right? And that tells you basically the projections will allow you to pick out from the huge sea of representation only which are allowed by the symmetry and which are invariant. And it's not invariant under a particular symmetry. If you have n number of symmetric groups, that object will be singlet under all of the symmetries, and that's what we are looking for actually. And that's what, because that is we can write down as a Lagrangian. So the parts, if I have a n number of symmetries, I can write down an operator in the Lagrangian if it is singlet under all of them, then only I can write it down, right? So that is what we are trying to do, and then we understand the first task for us would be to calculate the character function. And I told you that representations and character functions, there is a one-to-one correspondence, right? So how do we calculate the character function? There we actually map our connected compact group that we are dealing with their respective maximal torus. And what is maximal torus? It's basically maximal abelian subgroup, right? So if you have a, let's say, SU2, the rank is 1, so it's a T1, and T1 geometrically, how do you realize? It's a U1, right? Similarly, if you go for SU3, rank is 2, it's a T2, and T2 you can write down the 2 copies of U1. So similarly, if you are dealing with a SUN, where the rank is n minus 1, so that means basically the maximal torus Tn minus 1 is nothing but my n minus 1 copies of U1. Okay, and what is my E1? How do you write down E1? It's a e to the power I theta. And what is e to the power I theta? I can write down as a z, where z is unimodular. So I can parameterize E1 by a unimodular complex number. Okay, so you can think of, and parameters are basically nothing which are basically coordinate to explain that space. So my E1 space is basically parameterized by either theta or a unimodular complex number. So that's why for every E1 I associate a unimodular complex number which we call Zi for ith 1, right? And these are also named as my torus coordinates, right? So now we have learned how to calculate these character functions for SUN, okay, using this. Remember the van der Waals determinant in the denominator, and in the numerator there is something called in terms of epsilon to the power R1, R2, and those R1s, small R1s actually depend on the lambda and rho, where the rho is basically fixed from a given group, but lambda has a representation dependence, and that's through the lambda the representation dependence comes into the small r. So then we conclude that if we know the small r, we know basically the character function in terms of the epsilons. But there's a small catch was there. What was the catch? The catch was we can parameterize those character functions in terms of n minus 1 number of independent variables. But the way we introduce the epsilons, there's a overcounting. And that's why we put an additional constant that the product of all the epsilon i's are basically identity. And there we change our basis to z, and that's where we define something called the lowest dimension fundamental representations, and subtracting the Cartan matrix, simple poles rather in that representations to generate the weight tree, and that weight tree helps me to write down the relation between the epsilons variables and the z variables. So what we compute the character function in terms of the epsilon. Now using that relation I can again further rewrite that character function in terms of the z. But now I know if I am writing any character function correspond to SU2, whatever be the representations, that will be dependent only one variable because the rank is 1. If I am doing for the SU3, or any character function correspond to any representations of SU3 would be function of Z1 and Z2 and so on, right. So that's part we have done up to this part. Okay, yeah, any question? Okay, can you recall all those things now? So without doing the algebra, I just summarize whatever we have done this thing. So, but algebra is also important, and that will give you the calculational habit and all those things, but also it will give you basically the skeleton of what we have done so far. Okay, fine. Any question? Okay. So now what we will do, yes, last time what we did the character computation for the SU2, right? And if you remember, we computed the character function corresponding to SU2 doublet representations, and as I told you, the SU2 is a pseudodal representation. So 2 bar is a conjugate representation which will have the same character, and we have checked that thing also, right? What was the character? Z1 plus 1 by Z1. So that's why if you change Z1 to 1 by Z1, that structure remains invariant. That's why the 2 bar character is also the same. And then we calculate separately the SU2 adjoint character, right? What are the characters? Z1 square plus 1 by Z1 square, right? And then I argue that if my comment about the connection between the representations and the character functions is true, then all the properties that we have seen using the representations, that should also be reflected in terms of the characters, and one of them was Young tablet, right? So 2 cross 2 for the SU2 is 3 plus 1. So then if it is true, then I should be able to prove that if I take square of 2 SU2 character and I subtract the character of SU2 singlet, which is 1, I should be able to write down the character for SU2 3, and that is true. That's why they match among themselves, right? But today what we will do, we will try to compute the same thing but slightly more non-trivial object for the SU3, which is a now 2 variable object. Okay. So we'll do the example with the SU3, which is slightly non-trivial. Okay. So first thing that I am interested in, basically the rank is basically 2, because for SUN it's n minus 1, so rank is 2. Okay. And what are the fundamental representations? So what did I tell you? How to write down the fundamental representation for SUN? That you have n minus 1 tuple object is an array vector of n minus 1 element, and at a point only one element can be 1 and all of them have to be 0. And you start with first element to be 1, all element to be 0. So you get 1, 0. What are the next option you can have? 0, 1. Do you have any other option? No, right? So you can see you have only 2 fundamental representations, and that's what our counting tells us, that for any given group the number of fundamental representations is its rank. Okay. So if you look into this group 3 node that I have given, I think there's a formula given there how to calculate the dimensions using this Dinkin level. If you calculate, then you will see one is basically 3, another is basically 3 bar. Okay. So for us, what is my lowest dimension fundamental representations is basically my 1, 0, right? Because if you recall, so see, this is slightly involved, but all the steps will mimic exactly what we did for the SU2. So if you can recall SU2, we immediately write down this way. Okay. So now I told you what is the Dinkin diagram for SUN. What is the Dinkin diagram for SUN? N minus 1 number of blocks, and such that only 2 consecutive blocks are connected by a single handle. Right? There is no further complexity. So for SU3, do you agree that this is the Dinkin diagram? right? This is the Dynkin diagram, and once we know the Dynkin diagram, I should be able to immediately write down the Cartan matrix of this thing. How to write down the Cartan matrix for SU3? That okay, so I have A is the Cartan matrix, so I have two blobs, so these blobs represent in the Cartan matrix which element? The diagonal element. So and those diagonal elements are 2, so basically I write down 2, okay, and then I can see they are connected by a single line, so my off diagonal elements are -1, -1. So you see, if you know the Dynkin diagram, you can immediately write down the Cartan matrix. And once I write down the Cartan matrix, automatically I know this is my alpha 1 and this is my alpha 2. Okay. So see, whatever the ingredients I require, all I can write down for the SU3 now. And exactly we will see, we will not do anything new for SU3, because every time for defined group, if I have to do separate trick, that's not a good way of doing that. So we need to construct a very unified approach, okay, for any connected compact group. We will follow the same thing, and later when I discuss the SO2n or SO2n plus 1, we will see our approach will be exactly same. Of course, for them the Cartan matrix, the Dynkin diagrams, all are different, but I am talking about the steps, what you have to do after this. And now you can tell me what is the next step we can do after this to calculate the weight tree. That I have this lowest LDF, I will subtract my alpha 1 from there and then again alpha 2, and we will get the whole weight tree for that thing, right? Very good. So my L1 is basically my 1 0, L2 would be L1 minus alpha 1, which will be -1 1, and L3 would be L2 minus alpha 2, will be 0 -1. For the SU2 case, or for the generic SUN when you talk about, remember automatically we will stop when the last element will be -1 and all others basically 0. Okay, and you can see it's already exhausted alpha 1, alpha 2. You don't have any alpha 1, alpha 2. They're already. Okay. So are this step look familiar to you now? Are these the same exactly what we did for the SU2? Now for the SU2 we have only one element, right? But now it's a one dimensional array having a 2 vector. You can think like a vector, right? So now we are subtracting element by element, and when you subtract them, as you know, when you subtract a vector a1 minus a2, what happens? The I unit vector coefficient subtracted from the I unit vector is not ij, mixing is not there. Exactly the similar, this is like a vector subtraction you are performing. Okay, so that's why the positioning are important. You cannot just mix with different unit vector position and calling it the same vector, right? That's why the positions are important, and they are fixed by the Cartan matrix. Okay, fine. So now, if you use this relation, what will be my epsilon 1? Z1, because the first element is 0, and that's always true actually for any SUN. And then I have a epsilon 2 will be Z1 inverse Z2. Why Z2 is into the picture? Because it's a SU3. So I have two coordinates, and now you can see that there was not even a room for Z2 for the SU2, because there's only one. L1, L2 was just a single number element. And now you can see that for if I write down for SU4, there will be one more entry, right? And this will be one more non-zero entries will be there, and that will create the room for the Z3. But the relations, the way relation is being constructed, is basically following the same trajectory. It's getting more and more involved if you go for higher and higher symmetries. Okay. And then I have a epsilon 3, which is my Z2 inverse. Okay, fine. And as I know, there's another vector which is very important for us, and which is universal structure, is the rho vector. Remember, the R vector is basically lambda plus rho. So rho I can immediately write down this way. So rho I was n minus I. So for rho vector I can write down as a 2 1 0 for SU3. Right? So 3 minus 1, 3 minus 2, 3 minus 3. So I get 2, 1, 0. Okay. Fine. So now what I'll calculate? Delta epsilon. And what was the delta epsilon here? So epsilon 2, epsilon 1, epsilon 2, epsilon 4, 3. So this is the determinant you have to calculate. And this determinant appears where? In the character calculation. This is the Van Diamond determinant. This appears in the denominator. And as I told you, and you try to recall, that this is independent of the representations. And that's why I can immediately write down even before writing any representations. And this also appears another place where? We will see. That's called Haar measure. So the Haar measure actually are constituent from this thing. And because this doesn't have any representation dependence, so Haar measure will also doesn't have any representation dependent, right? And that is quite expected because Haar measure is the group space volume. It should not depend on the representations, right? Okay. So now if you calculate this, what you will find out as epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, epsilon 1 minus epsilon 3. So this product has a very universal structure like this. For any generic SUN, you can write it down this way. Okay. And now what you will do? You just replace this epsilon in terms of z. Okay. And then you get z1 minus z1 inverse z2. Then you write down z1 inverse z2 minus z2 inverse. And then z1 minus z2 inverse. Okay. So this is the Van Diamond determinant in terms of my z's. Okay. Up to this part, any question, any confusion, any step which is not clear to you? And do you feel that we are actually introducing something new step here apart from the SU2? The same step, right? It's the same thing we are doing. But instead of a one-dimensional object, now I am dealing with a two-dimensional object. That's the only difference. So if you know how to deal with Cartesian vector, you should not have any problem here. Okay, very good. So now we choose the representations 3. And by the way, many students actually get messed up with this thing. So let me make it very clear. When I talk about the representation 3, and if I stop, that it doesn't make any sense. Why? Because these 3-dimensional representations, I have to also mention it corresponds to which group. And that's what the many students make mistakes actually. Okay. For SU3, the 3-dimensional representations, its characteristics, its properties are completely different when I talk about the 3-dimensional representations of SU2. For example, you know the 3-dimensional representation of SU2 is the adjoint representations, and adjoint representations are by construction real. For SU2, all the representations are pseudo-real, but adjoint representations for any group are basically real representations. Okay. But SU3 3-dimension, is it real? No. And that's why we have a defined representation 3 bar, which is not as same as 3, right? But both are basically a same component object, psi 1, psi 2, psi 3. But their transformation, if it's under SU3 triplet, they will transform, and the transformation will be guided by the SU3 generators. The SU2 adjoint when I am writing, their transformation will be guided by the SU2 adjoint generators. So please keep in mind that just mentioning the dimensional representation doesn't make any sense until you mention the what is the group for that. And now you can understand if you go for higher representation, for example 10 dimension, it can come from SU2, it can come from SU4, it can come from a spin 10 group, which you call sometimes SO10 also. It's actually spin 10, right? So just mentioning the dimension, we cannot fix this property. And you have to also clear in mind that when you are speaking about some dimension, what is the group we are talking about. Okay, very good. So now, as I am working the SU3, so probably I will not mention again and again this is the 3-dimension of SU3, but of course this has nothing to do with the, at this point, with the 3-dimension of the SU2. That means if you say okay, the 3-dimension, so write down the SU2 characters, square it and subtract -1. It's not the SU3 character. Because even before doing the calculation, there's a fundamental difference. Because when you write down the character for this thing, this must be function of two coordinates, z1 and z2. And if you follow that, that's a function of only one coordinate for SU2. So there's a complete mismatch even before doing the calculations. Okay, so things sometimes get messed up in your young minds, but you have to be very careful about this, making the mistakes. Okay, so let's try to see how do we calculate basically this character for the three-dimensional representations of SU3. Okay, very good. So now this is the Young diagram for SU3 3-dimension, because for SU1 it's this thing. So now what I'll do, I'll take a shortcut rule of looking into and write the lambda like this. But you will not do this thing. You will repeat the same calculation by constructing the lambda. What was the procedure to calculate the lambda? Yes, so for that you need a information which I have not given yet, but you know already here. So let me mention this thing again. This is the Dinkin level. This is your A1, this is your A2, and we have learned how to write down the lambda 1, lambda 2, lambda 3 in terms of the A1, A2, A3. And as I told you, yes, yeah, you are not part of the class. You are not part of the class. Huh? Anyway, you are not part of this lecture, I know you. This is a physics class. Yeah. So now, as you know, when we write down the lambda, interestingly, in our construction, the number of entries in lambda is basically n for SUN. Right? So that means the last element is always 0. And that's why I commented on the last lecture, lambda n is 0 for all the non-trivial representations, and that also get reflected from the Young thing. And also you should be able to calculate when in terms of A1, A2. Okay, you will get this structure. So what you should do actually, given this Dinkin level, if you use the formalism that we discussed to calculate the lambda, you calculate this thing. This is your task. That's what the practice will be there. Okay, fine. So now I have this row vector here, right? So if I have a row vector, yes. Yeah, so what? You didn't hear me properly. What I said? I said all the non-trivial representations. Is singlet a non-trivial representations? No. Okay. So now I have a row vector, I have a lambda vector, right? So now if I have a lambda vector and row vector, if I have, what I can construct? Which vector I can construct? The R vector? This is the definition, right? And if I do that, I can write down 3, 1, 0. Do you agree? Right. So now, once I have this R, what I can construct? The numerator part. So now I am in a position to calculate the chi3, which is basically epsilon 3, epsilon 2, and epsilon to the power 0. So I am writing it's a 1 by the delta p. Okay. And this is a short form of the numerator determinant. The first one corresponds to the R1, R2, R3. So epsilon to 0 is the 1. And this will be written exactly very similar form, right? So let me write down once for this thing, epsilon cube, epsilon 1 square. Sorry, this is 1, right? Sorry. Epsilon 2 cube, epsilon 2, 1, epsilon 3 cube, 1 by delta p. Okay. And if I calculate this, I'll get in terms of epsilons, and then I'll replace the epsilons by the z's, and what I'll find out is following: z1 plus z2 by z1 plus 1 by z2. So this is the character for the SU3 3-dimensional representations. Okay. Up to this part, any question? Fine. So now let's calculate the 3 bar. So I have all this information. So yeah, so apart from this, I'll remove this quantities. Yeah. So now 3 bar. So what is the Young diagram for 3 bar?
Single box.
Single box? No. Single box is already 3. What is the 3 bar?
Box.
Yes. Why?
Because if you put n and it will be
Exactly. So for SUN, the n bar always represented by the n minus 1 number of vertical boxes. Okay. So just keep like a chant in your mind. Okay. So this is my 3 bar. So automatically lambda will be 1, 1, 0. But also my representation Dinkin level is basically 0, 1. So your job is to use that Dinkin level. Now your A1 is 0, A2 is 1. So use this information and calculate the lambda, and you should be able to get this lambda as a 1, 1, 0. And you can see this is a different lambda than this one. Of course, my R is also be different than, because my rho is same, right? So then here R is my where is it? 3, 2, 0. Okay. So what I can calculate now, okay, let me calculate here. It will be very interesting to observe here. So my chi 3 bar would be epsilon cube epsilon 2 1 by delta of E. And I am not explaining now how to calculate this thing, because this is already I have explained. Okay, and this is the steps you must do, and if you cannot do, then I am sorry. So if you calculate this thing and again convert in terms of Z, what you will find out is the following: Z2 plus Z1 by Z2 plus 1 by Z1. Can you find something interesting here? Exactly. So now, so chi 3 is related by the interchange of Z1 and Z2. So if I change my Z1 and Z2 and Z2 to Z1, okay, I get exactly the basically the chi 3. Okay, and this is not only for SU3, but this also get reflected where? For any other SUN, when you have a n character for n and it's anti-fundamental representation. So if you have a suitably change those z's, okay, pairwise, you will get them. Okay. Fine. So what is the next representation that we are interested to compute? Any guess? Adjoint? Right. So what is the adjoint representations for SU3? Huh? Which one?
The weighting will be different from what we got.
No. Because the weight tree depends on the lowest dimensional fundamental representations. Because see, if you remember now, okay, that's a good point. You have raised this thing. So let's go back to again SU2. So when you have a SU2, we have a 3-dimensional representations whose Dinkin level was 2, right? Because fundamental lowest dimension is a 1, so this is 2. But did we construct a weight tree for that? No, because weight. So this is the relation that is what being derived from the weight tree, and this relation is independent of the dimension of the representations. Okay, Dipanshu, is it clear now? Okay. Huh? Hmm. Yeah, because 3 bar will, what is the weight tree if you think of? Weight tree is nothing but the component states inside that multiplet. Right? So if you see, when you subtract them, you basically, so when you say it's an 8-dimensional object, why is it 8-dimensional object? First of all, why is it 3-dimensional object? Because if I start with the lowest dimension fundamental representations and I subtract the possible way of alpha 1 and alpha 2, okay, until all the elements I reach out to that 0, 0, minus 1, okay, I'll get different kind of states in between, and if I count the number of states that exactly match the dimensions. And that's why if you want to construct the weight tree corresponding to 8 dimension, then you'll find out that for the fundamental anti-fundamental, you are allowed to subtract your alpha 1 alpha 2 only once, but there you can use the repetitively alpha 1 alpha 2 unless you reach out to this thing. But if you do it properly, you will see starting from 8-dimensional weight. So it is 8, then the Dinkin level is 1, 1. Okay, and if you start from here, you reach the 1 minus 1, and in between you will construct 8 such states. And now if I think about like a quantum, an object, let's say a psi has a psi 1, psi 2, psi 3, psi 4. Each such states correspond to one psi 1, psi 2, psi 3, psi 4 and psi 8. So remember, so basically when you write down basically the quantum numbers, for example SU2 doublet, when you write down, what is the same for them? The isospin. What is different for them? Projection of the isospin or the third component, right? But for the SU2 spin half, you have only 2 such states are allowed. Okay. Now when I am writing SU3 8-dimensional representations, that means it represents psi 1, psi 2, psi 3 up to psi 8. The 8 objects you can club them together. Okay. In such a way, now what are their corresponding Dinkin level, if you think of that way, that you will get from the weight tree of 8. So the number of entries in the weight tree is equivalent to the dimension of the representations, and that's the beauty of the weight tree actually. And that is how actually, I mean, we physicists actually use mathematics in a more little bit rigorously. So we just first associate the dimension and all those things. But how do I know this is 8 dimension? Let's say I am throwing you some Dinkin level and I ask you what is the dimension. If you don't use that formula, what you do, you start with the Dinkin level, you then subtract the Cartan rows or the simple roots, okay, and there you will find out until you reach basically the all negative in the end 1 minus 1 kind of states, okay. You basically generate in the process 8 such states, and if you get some 8 such states, it automatically tell you that these Dinkin level correspond to the a representation whose dimension is 8. Okay, but I didn't want to go there because I am using only the weight tree of the lowest dimension representation such that I can extract this information, but it has more implications in a representation. Yeah. No, that's why I said actually. Okay. The thing is, for the fundamental representations, you can, especially the lowest dimension, you will be allowed to subtract only once. If you subtract twice, you will get a negative root. So I can subtract alpha 1, alpha 2 as many times as I can without creating a negative states, roots. So that is the only condition I have. So that's why if you go for higher dimension, the possibility of subtracting and now you will see sometimes you will end up getting a degenerate state by subtracting alpha and alpha to both. So they will fall on each other. So there's a very beautiful structure comes from the weight tree. Okay, so what I'll do, remind me next class, I'll show you how the weight tree of 8 dimension actually being constructed. That's a very beautiful construction. Okay, and then you realize that 8 distinct states you will find out. For example, I mean, remember in the quantum mechanics, in angular momentum, when we write down the Jm, we have the half, 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 minus half. These are distinct states, but we can club them half, minus, and half, half to write a doublet. Similarly, you can think of like those kind of states, okay, which you club them, making a multiplet, and the dimension of the multiplet is 8 dimension. Yeah.
We started from the lowest dimension that was going here. So when you get if you again apply
First element will be negative. Yes, that's not allowed because I have to remember I have to constant on the positive roots.
Is it like in quantum mechanics we have from J to minus J and we cannot go beyond minus J?
No, so there the thing is basically because we are so that is basically those states are basically getting annihilated there. That's why we cannot reach out even there. And there the states are connected to each other by L plus or L minus, raising and lowering upward, right? That's the annihilation is there. Okay. So if you use the action of alpha 1 and if you say my positive roots form a close, okay, where the negative roots are not allowed, then you can subtract this alpha 1 alpha 2 like that only. But let's say you want to constant all the states, positive and negative, then you can create that thing. But you will get all the negative states which is a pairwise with the positive one. Okay. So in the weight tree, we look for those only. Okay. Yeah. Okay. So now we have this 8-dimensional representation. So what is the Young diagram for SU3? This one, do you remember? Can you calculate the dimension of this? What is this? It's the 8-dimensional object, right? 3, 4, 2. So 3, 4, 2, and then 3, 1, 1. Basically 2, 8. Okay. So this is the SU3 adjoint representation. So I have that. And then I can write down my lambda vector as 2, 1, 0. And again, as I told you that I have my A1, A2 here. So your task is to use the lambda in terms of A1, A2. From there, you cross check this thing. Again, you can see this is a non-trivial representation, so lambda n equal to 0. Okay. And this is my row vector again, so I can write down my R as my lambda plus rho 0, 4, 2, 0. Right? So then, what will be my chi 8? Chi 8 will be epsilon to the power 4, epsilon 2, 1, and then again this is the same delta epsilon. Right? And then if you calculate this thing, what you will find out? This Z1 Z2 plus 1 by Z1 Z2 plus 2 plus Z1 by Z2 square plus Z1 square by Z2 plus Z2 by Z1 square plus Z2 square by Z1. This is a very convoluted, complicated function of Z1, Z2. You get this thing. Okay. So you must check all this result actually. And then also, if 2 cross 2 equal to 3 plus 1, so the chi 3 of SU2 equal to chi 2 square minus 1, that is satisfied, then I am expecting this also have a similar kind of implications. Right? And what was that? Because for SU3, okay, let me have a special. For SU3, I know 3 cross 3 bar is 8 plus 1. So if it is so, then I should be able to cross check that this is chi3 times chi3 bar minus 1. Okay. So now I have computed chi3, I have computed chi3 bar, and what is the character for singlet? What is the character for singlet? 1, right? Simple. So now if you multiply and then subtract 1, you should get this one. So again, that representations information I can actually extract here and I can verify. And similarly, you can construct the other higher representation and so on. Yes. Sorry? Yes. Please. You are right. Bolo? Yeah. It remains invariant, right? Why?
Because it is I3 dot I3 star. So like if we swap it, it becomes I3 star dot I3.
That's a mathematical observation, but I am asking you on a more physics oriented thing because this adjoint is real. Right? So that's why. So you can think of like a Z1 is more biased to particle and this, and if you take a composite kind of state we create, and if you take a real state, that has to be close among themselves. Right? Because 8 bar is basically 8. And that's get reflected here. Very good. You raised this point. So this is symmetric in Z1, Z2 interchange. And this is not only for SU3, and also, for example, if you go to the SU2 case, if you change Z1 to Z1 inverse, that is symmetric. Right? Z1 square plus 1 by Z1 square plus 1. So there you have one coordinate, but still you can make that. Z1 and Z1 inverse are connected to each other. So if you go for any arbitrary group, if they adjoint representations, their inverse coordinates are basically symmetric among themselves. Okay. Any other question? Yeah, please. Which one? Yes. 1, 1. This is this is actually, I have shared you something called the group theory note. Some glimpse of this thing is there, but this requires more understanding, and I require at least 10 lectures to explain this thing, which I do not have that much time. So you can think of at this point this thing, and if you want to get a very good source of reference from where Dynkin level of most of the representations you will work in your life are given, it's a fantastic reference, and which is like a Bible for all of us who work in grand unified theory. It's a group theory for unified model building. It's a physics report by Paul Langecker. Okay. And its small version is nothing but that book by the Raymond. The Raymond books is a smaller version of this one. Okay. So that actually, whatever the group connected compare group we are talking about, in the extension group and so on, it has all the list of this thing, Dynkin level and all this thing. Yeah. Okay. So I hope that you will be able to now compute the characters for any representation for SUN. Right? Okay. So the part of the assignment will be based on these things. I will give you some random groups, okay, of course SUN, and I will ask you to calculate the characters functions. Okay. So now what will be the next part of the assignment that I am going to discuss, the calculate the Haar measure. Yeah. Yeah, if you have any question about the characters, please ask now. Okay, so now our topic is to how to calculate the Haar measure. Okay, so as I told you, the Haar measure is nothing but is a group space volume element. Okay, and you have to calculate in terms of this torus coordinates, right? So for SUN, the Haar measure is written in this following form. So d mu of SUN is 1 by 2 pi I to the power n minus 1 n factorial, and then you have close line integral L equal to 1 to n minus 1 dZL by ZL delta of epsilon inverse. Yeah, I am coming to that. I will explain the formula. So this is the definition. Okay. Now, first you can see that this is a basically very mixed definition. This measure is basically in terms of z and this is epsilon, but this is at this point now you know how to relate between epsilon and z. So I can always write down this delta epsilon and this thing in terms of right. So I can just connect that thing. So I'll equivalently write down everything in terms of z coordinate first of all. Fine. And what is this individual this thing? This is our known the Van der Waals determinant. And what is delta A epsilon inverse? That if your delta E is, let's say, of this following form, then delta epsilon inverse would be minus 2, minus 1, 1. Just replace epsilon by 1 by epsilon. That means all the powers would be negative now. Okay. So that is the definition of delta epsilon inverse. So that will give you this quantity, and this is dZL by ZL. If you recall your first lecture of the Hilbert series, this is exactly the Haar measure of the U1. And as I told you, basically the T n minus 1 is basically n minus 1 copies of U1. So this factor comes and represent basically U1, mimicking U1 part. And this is the non-trivial part because it is not exactly U1. For U1, this becomes more trivial identity 1, this part. So this part carry the information about it's a SU2 or SU3 or SU4, but because now writing in terms of U1, so this structure reminds us what we learned very first line about the Hilbert series, the U1 part. Okay. And then you can see that once you have this structure, okay, and now we can use the residue formula here. Okay. So what we'll do, this part will be glued with the prefixes. Because this is not the only, it's not ending here, na. We're calculating this way, right? So this integral we are not performing, it's like an open integral, you can think of that way. We have to glue the prefixes here inside the integrand and then we'll perform the integral. So initially I wrote down this thing to make you understand that where this closed line integral comes in the prefixes. Okay. But if I am writing a volume element, okay, so better I drop this integral sign. So once I glue this with the prefixes, then I put the integral sign. Yeah.
This looks like when you transform the coordinates, like or like giving so can I think of it in that sense? Like you are kind of going from U1 to like that. Thinking of it basically as
So actually you are not going from E1 to this thing. So basically, so what you are doing, you are writing any SUN in terms of n copies of E1, but it is something more than that in the volume element. Because when you talk about the SUN volume is not just the n copies of E1 volume, it's something more than that. And the more is basically captured here. If it's identity, then it's just a n copies of E1. But n copies of E1 volume is not the SUN volume element. Yeah. It will represent only n copies of disjoint E1. Yeah. So that's what I'm saying. It's a n copies of E1, but that is not going to represent you SUN. Yeah, that's n copies of E1. Yeah, for example, if I have a let's say theory, sometimes as you do in the particle physics, like standard model extend by 2 E1, or so 1 E1, let's say E1, you have a 1 E1 hypercharge, and then let's say E1 some baryon number. So in that particular case, it will be like a dz by z1, dz2 by z2, and they are not talking to each other because they are 2 E1. But the SU2 will or SU3 will have another dz, but there will be associated this kind of non-trivial van der Waals determinant, but this is identity for that E1y and E1b, but not for SU2 or SU3. So that's why n copies of E1 volume element is not just the SU1 volume element. That's a mismatch and compensated by that thing. Okay. Okay. So now, so now you can see that these n fact. So this is basically just to normalize your thing, because the residue formula comes with the 1 by 2 pi I. So either you forget about the 2 pi completely, or you just keep it just to normalize this thing, because when you calculate that, otherwise the 2 pi I should cancel. Okay, you get a real number. And this n factorial is there to capture the residue formula for number of z's, more than once you are occurring. It's not a simple pole, but again the z again and again they are repeating mainly there, so you have to take care about those items also. So that's why this thing. But eventually it's like a what you have learned in math methods 1, the complex integral. Once you know the character function and this thing, eventually you have to perform that only, nothing more than that. Let's see how does it look like. So let's do some example. Yeah. Which one? No, this is n factorial. Because this is as a normalizations of this volume element. So you have to normalize the volume element. Okay, this is from the normalizations. No, that comes from this n minus 1. So because for each z you have to calculate the poles. So that's why if you have a n minus 1 number of z, you can get maximum simple pole in terms of n minus 1 coordinate. Okay, and that's why it get cancelled by this thing. But this is with the how to normalize this thing. This is just from the normalizations come to the picture. This is not using that thing. Any other question? Okay. So now let's do example for the SU2. So delta of epsilon is basically Z1 minus Z1 inverse. So delta of epsilon inverse will be Z1 inverse minus Z1. Just to change the, as I told you, the coordinate inverse. So you get and that one. So it's easy to, once you calculate this one, it is easy. Just change all the Zi by Zi inverse. You get that one. So eventually I get delta epsilon inverse as my 1 minus 1 by Z1 square into 1 minus Z1 square. I mean, it captures all the information is there actually. So you can just single out because normalizations of the volume element, because it also related how to normalize the characters. No? No, because I have to satisfy this definition. Yeah. So this is the normalization I'm talking about. That dictates you basically this has to be n factorial. Del Taylor, yeah. Del Taylor. Okay, so they are orthogonal, orthonormal. So you can remove n factorial from there, but you have to suitably then multiply in your character this thing. The way we define the character, it requires this thing to get this satisfied. No. That is basically to project out this thing, but the core relation is basically orthonormality of the character function. When I'm writing defining the wild character, okay, I just cannot multiply by any random number, na? The character function. If I write down a 5, let's say, there has to be compensated somewhere. So I have to use the orthonormal basis. Yes. No, the normalization basis is this one. And this fix the way once I fix the wild character formula, it automatically fix how to normalize the d mu. Chi for the singlet. Yeah. No. Also, see, when I write down the wild character formula, okay, if I write down a random number with the wild character formula, all my things will change. So the way I defining the wild character formula, it has to be on par with this d mu definition. The d mu definition and the wild character formula, they are not talking to each other. It cannot be. Okay. So when you, for example, in quantum mechanics, when you just let's say psi, when you are writing, so now you have a fixed volume element. Okay. So for a given volume element, you can fix this thing. If I change my wave function randomly, then of course that has to be scaled, and that scale factor I can absorb in the definition of the volume element now. So all together has to satisfy one. Now there is a freedom that how do, for example, if I remove this kind of thing, but I can rescale my character. What I am calling a character 1 for the singlet, I call it a root n. I can always do that thing. That much freedom I have. So where I will dump, that's up to me. How do I write down the character functions? So now I can write down d mu of SU2 as 1 by 2 factorial 2 pi I dz1 by z1 delta epsilon inverse, which is basically 1 by 2 pi I dz1 by z1 1 minus z1 square into 1 by z1 square. Okay. So this is your SU2 higher measure. Okay. And now you can see this is only function of one coordinate. Okay. So now plethysticks, the representation also have a one coordinate. They will glue with them. Okay. And eventually then you will use the residue formula. So you will look for, if you look into only SU2, you will look for all this after doing the multiplication. What are the structures that gives you basically, if you, because Z1 is already outside, so multiply plethysticks here, this quantity and the plethysticks exponent, giving you some Z1 independent term, and only those terms will be invariant here. Okay. Similarly now for the SU3, when I do that, I'll calculate d mu SU3, will be 1 by 3 factorial 1 by 2 pi I whole square dz1 by z1 dz2 by z2 and delta epsilon inverse now. And here the delta epsilon for SU3 as we have calculated while calculating the characters, z1 minus z1 inverse z2, then I have a z1 inverse z2 minus z2 inverse, and then z1 minus z2 inverse. Okay. So if I do this thing, what I'll find out the SU3 character to be 1 by 6 2 pi I whole square dz1 by z1 z2 then 1 minus z1 z2 1 by z1 z2 1 minus z1 by z2 square 1 minus z2 square by z1 1 minus z2 by z1 square 1 minus z1 square by z2. Okay, so this is the higher measure of the SU3. So now already I hope you are getting the feeling that why it is become cumbersome if I give you some SU3 representations and ask you to project out the invariants. But it's a very convoluted object, okay, and that's why there is an algorithm based on that has been developed and that has been written in terms of open source program. It is called group invariant polynomial for, I think there is a okay, so this is an open source program which you can use. It's a basically mathematical based program where you can give the representation at Dynkin level, okay, and then you should be able to write, it will give you the characters and the hard measure for given group and the representations, okay. So, but don't use immediately this thing. What you should do, I will give the assignment, okay, you will calculate them and then you will verify them using this program. Okay. Fine. Okay, any question? So, for the time being, this was what for the internal symmetry group I was planning to discuss. So, we will come back to this SO2 and SO2n plus 1 later whenever required. Okay. In the next class onward, I will move to basically the space-time symmetry, because it will be little bit more non-trivial structures are there. Okay. But we gradually try to learn whatever. But as I told you before, in the next lecture, please brush up to this part, okay, and such that now I will use this result for them. I am not going to explain how do I compute. I will assume all of you automatically recall how those things are being computed, because there are some new techniques have been discussed based on this older one. Okay, fine up to this part, and please learn the necessary mathematics, especially the represent theory. I shared the group theory note, so some things are there. Okay. Okay then, thank you.